Welcome back to the deep dive. So we got a whole stack of research from you on industrial cutting, and the core dilemma seems really clear. If you're running a fabrication shop, you have to cut metal efficiently, right, and quickly. But if you pick the wrong laser, or you just stick with older tech, you can waste a ton of money.
That is the problem, isn't it? And that's what we're diving into. We've been through a lot of material comparing the two main players, fiber laser cutters and, the traditional CO lasers.
And for anyone in metal manufacturing, the conclusion in all the data we saw was pretty one-sided.
It's unanimous. Fiber technology is just dominating the modern market. There's really no contest in that space anymore.
Okay, so our mission in this deep dive is to unpack exactly why. We're not just looking at the sales pitch. We want to look at the physics, the actual performance on the shop floor, and maybe most importantly, the bottom line, the cost.
Absolutely. And to be fair, co-lasers still have their place. They are fantastic for non-metals. So think wood, plastics, acrylics, things that fiber lasers actually have a tough time with.
Sure.
But the second you step into the world of metal fabrication, which is, super competitive, you need high speed, low overhead, that's where the gap between the two just becomes massive.
Okay, so let's start at the very beginning then, the fundamental physics. What makes these two technologies so different? It all starts with the wavelength, right?
It all starts with the wavelength. It's about what the metal actually wants to absorb. If you've ever tried to cut something really reflective, like, say, polished aluminum or copper...
Yeah, that's a nightmare.
It's a huge problem. With older systems, the energy from the laser just bounces right off, and that reflection is really dangerous. It can shoot right back into the machine's optics and, cause a very expensive shutdown.
And that's where the CO laser's specific wavelength becomes a problem.
Exactly. A co-laser operates at 10.6 micrometers. That's in the far infrared part of the spectrum. And at that wavelength, a metal surface is basically a mirror. The absorption is terrible. You're just wasting huge amounts of energy trying to punch through that reflector shield.
You're just blasting it.
They're blasting it. Whereas the fiber laser, it works at a much, much shorter wavelength.
And that's the whole key.
That's the key. The fiber laser is down at 1.06 micrometers, so 10 times shorter. It's in the near infrared. And that might not sound like a huge jump, but in terms of physics, it changes everything.
Right. That's the real aha moment.
Yeah.
So why does making the wavelength 10 times shorter suddenly make metal absorb the energy instead of reflecting it?
It's all about how that light energy talks to the material. The shorter wavelength, the 1.06, it couples really, really easily with what they call the free electrons inside the metal. So when that beam hits, the energy is absorbed almost instantly. Reflection drops dramatically, and you don't have that risk of back reflection damaging the machine. That's the real reason fiber lasers can just slice through copper and aluminum, materials that would basically cripple a Euro system.
So you don't have to, pre-treat the surface or just crank up the power to insane levels to get it started?
Not at all. The energy transfer is immediate. There is a fascinating detail in the research about stainless steel, actually.
Okay.
The short, intense wavelength from the fiber laser creates what they call a micro-level light trapping structure. Basically, the spot where the laser hits instantly turns black.
And anything black absorbs light.
Absorbs light way better than something shiny, so it kind of helps itself along, creating the perfect condition for melting to start immediately.
So just to sum up the science then.
Yeah.
Euro is far infrared, low absorption, danger is on reflective metals. Fiber is near infrared, high absorption, and cuts pretty much everything because of that better electron coupling.
That's the foundation for everything that follows.
Right. But physics is one thing. What does it mean on the factory floor? This is where it gets interesting for, shop managers. Production speed.
This is where you see the difference between being competitive and, frankly, being left behind. If you're working with sheet metal under, say, 6 millimeters thick, fiber is just. It's fundamentally faster.
How much faster are we talking?
We're often talking 3 to 5 times faster than a comparable co-Urus machine. And that speed, that directly translates into getting orders out the door and a much lower cost per part.
And it's not just the absorption. I read it's also about how tightly you can focus that beam.
Right, absolutely. Absorption is half the story.
Mm-hmm.
Power density is the other. Because the fiber wavelength is shorter, you can focus it down to a tiny, tiny spot, much smaller than a co-Euro beam. The analogy one source used was perfect.
The needle in the thumb.
Exactly. It's like trying to break a piece of wood by pressing on it with your thumb versus pressing on it with a needle.
You're putting the same force into a much smaller area.
And that incredible power density vaporizes the metal instantly instead of slowly melting it. It's so efficient that a A 1.5 kilowatt fiber machine can often match the cutting speed of a 3 kilowatt CHU machine.
Wow. So you're getting the output of a 3 kilowatt machine for, half the rated power. That's a huge deal.
It is. You're getting more production with less power. And for those high-volume jobs like 1 to 3 millimeter stainless steel, fiber is usually 2 to 3 times faster. In some cases, for thin foils and automotive, you can see speeds up to 20 meters a minute.
20 meters. And a co-machine would be topping out at what, 4 or 5?
If you're lucky, yeah, it's a complete game changer for your daily output.
Now, normally when you talk about going that fast in manufacturing, quality takes a hit. But here, the speed actually seems to help the edge quality. How does that work?
Because it's so fast, the heat doesn't have time to spread. It doesn't soak into the rest of the material. We talk about the heat affected zone, or HAZ.
A smaller HAZ is better.
Much better.
Yeah.
It means less thermal stress, a cleaner cut, and way fewer burrs on the edge.
Which means less cleanup afterwards, less grinding, less labor.
Exactly. You save time on the cut, and you save time in post-processing. Now, we should say, Keo does still have one tiny niche. For very, very thick plates, maybe over 8 millimeters, where you need a perfectly smooth edge, but for almost everything else, fiber wins.
Okay, so better absorption, much faster speed. But what about the cost to run the thing? Let's talk about the electric bill.
This might be the most powerful argument for fiber, especially now with energy costs going up. It comes down to a metric called electro-optical conversion efficiency. Or, wall plug efficiency.
Basically, how much of the electricity you pay for actually turns into a laser beam versus just waste heat.
Right. And the numbers are pretty shocking. Fiber lasers run at about 25 to 30% efficiency, sometimes higher on the newest models.
And Kiro.
Kuros are stuck down at around 8 to 10%, which is horribly inefficient.
I like the financial analogy from one of the articles. Can you walk us through that?
Yeah, it really puts it in perspective. If you spend $100 on electricity for your co-laser, only about $10 of that actually becomes cutting energy.
And the other $90.
Just waste heat. One of the engineers in the research said it perfectly. He called the Co-Euro machine a gigantic, powerful heater that also happens to cut metal.
That's, yeah.
Whereas a fiber laser at 30% efficiency gives you 3 times the cutting power for the exact same $100 electricity bill.
And the costs don't stop there. Because you have to get rid of all that heat. You're paying to make heat, then you're paying more to cool everything down.
That's a huge secondary saving. Co-machines need these massive water chillers to keep from overheating, and that chiller is a huge power hog on its own.
Right.
Fiber lasers run so much cooler that they use a much smaller chiller, so you're saving a ton of electricity on the cooling side, too.
And what about just, starting the machine up idle time?
Another good point. A Coco laser needs to warm up. Usually 10, maybe 20 minutes for the gas to stabilize before you can get a good cut. All that time, it's burning power, but making 0 parts.
But a fiber laser is instant on.
It's solid state.
Yeah.
You flip the switch, and you're cutting. There's no idle energy waste at all.
So when you add it all up, the laser itself, the chiller, everything, the difference is massive.
A fiber laser uses about 20 to 30% of the total power of a Co-Euro machine doing the same job. The data we saw showed that over 5 years, just the utility savings alone can pay for a huge chunk of the machine's initial cost.
Okay, we've got better science, better performance, way lower running costs. What about the final piece of the puzzle? Keeping the machine running, maintenance and downtime.
And this is where Co-Euro systems are a real pain point for maintenance crews. The whole system relies on this complex path of external mirrors to guide the beam from the source to the cutting head.
And those mirrors are exposed, they get dirty, they get knocked out of alignment.
All the time. A little bit of vibration, some dust, and your alignment is off, the beam quality drops, and suddenly your machine is down.
And production stops.
For days sometimes, while a specialist comes in to realign everything. Not to mention, you have laser gas mixtures to buy, high voltage turbines that wear out. It's a mechanical beast.
And the fiber laser solution is just simpler.
Fundamentally simpler. It's a solid-state device, no moving parts inside the source. It's a digital approach versus an analog-mechanical one.
And critically, no external beam path.
That's the sanity saver. The mirror alignment is just gone. The beam travels through a sealed, flexible glass fiber cable. One article called it a garden hose for light.
I like that.
You can move it, coil it, it doesn't matter. The beam is perfectly contained. So all that maintenance, the gas mixing, the delicate alignment, it's all eliminated.
Let's talk about the lifespan. That was another huge number.
The difference is staggering, yeah. A Co-Euro tube might last 20,000, maybe 30,000 hours, And then you are looking at a massive bill for an overhaul.
But the fiber modules,
They're rated for over 100,000 hours.
100,000. That's more than a decade of constant heavy use.
It completely changes how you plan for capital expenditure. The source is sealed, it's solid state. The only real maintenance is just wiping the protective glass on the cutting head once in a while. It's designed for maximum uptime.
Okay, so let's try to synthesize all of this.
Sure, I think it boils down to 4 key things. First, you have the superior wavelength, 1.06 micrometers, which means better absorption. Second, you get much higher speeds, up to 5 times faster, because of that tiny, high-density focus spot.
Then the efficiency.
Third, yes, the huge energy efficiency, 30% versus maybe 10 for Euros. And finally, the solid-state durability, that 100,000-hour lifespan with almost no maintenance.
So what this means for you, the listener, is that the shift to fiber in metal fabrication, it isn't really a choice anymore. It's an economic inevitability. It's driven by physics, and it leads directly to better performance, higher profits, and a lot less downtime.
Exactly. And that actually leads to one final thought, something that builds on all this. We talked about that huge efficiency gap, right? 30% versus 10%.
Yeah.
Well, think about the future. If the global focus on energy consumption and carbon footprints keeps driving electricity prices up, how quickly does the Euro laser become completely unsustainable to operate?
Even for that tiny niche of cutting really thick plate.
Even for that, the economic pressure from the utility bills alone, plus the constant maintenance, might just make running those old, energy-hungry machines fiscally irresponsible. It could force the entire market over to fiber even faster than anyone is predicting right now.